So, good morning everyone. So, last class we were discussing Khrapchenko's theorem. So, let me state the theorem from that we saw last time. So, this is a theorem which is used to give a lower bound on functions. Okay. So, what does this theorem say? So, the theorem says that suppose if you have a Boolean function f, okay. So, let f be a function from zero 1 to the power n to 0 1. So, f is a Boolean function and let A be a subset of f inverse 0 and B be a subset of f inverse 1. So, basically A is some set of inputs which map to 0 and B is some set of inputs which map to 1. Then what we have is that the size of the star size of the function f over the basis and or and not is at least, what was the quantity? N a b whole square divided by the cardinality of A times the cardinality of B. This is what we stated last time. So, let us try to understand this once more. So, what we are saying is that NAB is basically the number of tuples, okay, from A cross B. Okay, so, the first element of the tuple is from A, the second element of the tuple is from B. So, the number of tuples of the form, let us say sigma comma tau, such that the Hamming distance between sigma and tau is exactly 1. Okay. So, basically intuitively these are like two strings which are almost the same except for one bit, they differ exactly in one bit. And what this theorem says is that if we have a function f and if we take any two sets A and B such that A maps to 0 and B maps to 1, then this size of the function, the star size means that the number of AND and OR gates. Okay. So, when we say star size, we are counting how many AND and OR gates are there, and L is the formula. Okay. So, L is the size of the formula for F. So, the smallest formula, if I count the number of AND and OR gates for F, will have size at least this much. Okay. So, how do we prove this theorem? So, any questions? Okay. So, let us try to yes, exactly, and for any, not just all the input strings, but if I take any subset A and B of the input strings, if they are similar, what that means that NAB will be larger, which means that they will require larger formula. Yes, so that is the intuition. So, how do we prove this? So, what we will prove, as I said last time, is basically we will prove about the leaf size. So, we will show that the we will show that the leaf size of f is at most this quantity. So, what is leaf size? Leaf size is the number of leaves in a formula, and why does this why is this sufficient? Because we know that if we have any tree, if we have any binary tree, then the number of leaves is one more than the actually the result is this is equal to this minus 1, this is the precise result, and the number of leaves is basically one more than the number of internal nodes. That is why it is enough to show it for the leaves. Okay. So, the proof is by induction on the size of phi. Okay. So, let me write it over here. We will prove by induction on phi. So, firstly base case. So, the base case is when let us say phi is a some single variable xi, okay. It does not have any gates. So, then what does this mean? Now, what this means is that if I take any sigma from A, okay. So, suppose if I take any sigma belonging to A, okay, then what is, how large can n A be? I mean, how large can this n A comma B be? Okay. So, if sigma is in A, then observe that, well, look at the variable xi belonging to sigma. Okay. So, look at that position. Okay. So, that is the only position which can change. So, if sigma belongs to A means that sigma is mapped to 0, right. Now, if I want to consider sigma, I mean if I want to consider another input which goes to 1, which differs only in one position from sigma, that can only be at the position xi, because that is the only thing which is affecting the input, right. So, if sigma belongs to A, then the n A comma B will be equal to n A comma B is in fact one second, is at most the size of A. Okay. So, as I said, since sigma has at most one neighbor in B. Okay. And by the same argument, we can say that n A B is at most the size of B. So, now if n A B is at most size of A and B, therefore, the result clearly follows. Okay. Now, let us look at the induction case. So, the induction case we will divide it into 3 parts. Okay. So, the first part is when suppose let us say phi is equal to naught of some formula psi. Okay. So, if phi is naught of psi, now let us consider the possibilities. So, suppose if I have a set A which is a subset of phi inverse 0, what can I say about A with respect to psi? So, A is basically a set of inputs which go to 0 in this formula phi, right. So, with respect to psi, it would go to 1, right. So, if A is a subset of this, it implies that A is a subset of psi inverse 1. Okay. And similarly, if I have B which is a subset of phi inverse 1, it implies that B is a subset of psi inverse 0, and this is if and only if. Okay. the same thing holds for the opposite direction as well. So, therefore, this proves the and now psi is a smaller formula because it has one less gate. Okay. Therefore, by induction I know that the formula is true for psi, hence we are done. So, if I have a formula which is not of some other formula, then it follows by this observation. Okay. Now, let us look at the more interesting case when suppose phi is equal to and of something. Okay. So, let us say it is, sorry, let me just write it a little lower. Phi is equal to psi and some formula chi. Okay. So, if this is the case, let us try to rewrite this. So, suppose if I have A, which is a subset of phi inverse 0, okay, which means that all inputs in A map to 0, then what do we have? That A is a subset of. So, what can I say about A with respect to psi and chi? Psi inverse 0 . So, suppose if I have an input, so what does the AND mean? So, if I have a 0 over here or a 0 over here, it is a 0 over here, right. So, if one of these two go to 0, then it will go to 0. So, it will be union, not intersection. Okay. So, if either psi maps to 0, I mean if I have an input which is mapped to 0 by either psi or by chi, then I know that phi will map it to 0 and hence it would belong to A. Okay. Now, if I take B such that phi, which is a subset of phi inverse 1, what can I say about B over here? So, when is an input mapped to 1? So, if I have an if both of them are 1, right. So, what should it be? So, it will be phi inverse 1 intersection with chi inverse 1. Once again, this is if and only if, right. So, if either of them goes to 0, then this would go to 0, and if both of them go to 1, this will be 1, right. So, now we know how to divide. So, we know how to kind of state an input in terms of the sub formula over here. So, now let us try to let us just establish some notation before we proceed. So, so what notation do I have? So, let A of phi be a subset of phi inverse 0 and A of chi be a subset of chi inverse 0 such that if phi intersection with A chi is disjoint, okay, they do not have any common element, and if psi union with A chi is my set A. So, all I am saying is that I take A and I just divide it, I just partition it into two parts, A psi and A chi, okay, where A psi is basically all those inputs which takes psi to 0 and a chi is all those inputs which take chi to 0. Now, there can be some common elements in between. Okay. So, there can be some inputs which take both psi and chi to 0. I can put them in either one. I can decide to put it in either one, it does not matter, but I just want to ensure that there are no common elements. Okay. This is any partition, and I will also use another notation. I will use n psi to be n of a psi comma b and n chi to be equal to n of a chi comma b. Okay. Now, how many neighbors or how many triplets are there which are neighbors between a chi and b, and how many triplets or how many tuples are there which are neighbors between a chi and b, right. So, what is the relation between n a b and n psi and n chi? So, what was n a b? N a b is all those tuples such that the first element belongs to A and the second element belongs to B and they are neighbors. Now, I am partitioning A into A psi and A chi, right. So, what would be the relation? Exactly. So, n a b is nothing but n psi plus n chi, right, because each tuple I can decide to put it either in this set or in this set, okay, each tuple belonging over here. Okay. So, now we have established the notation, now we can get to the proof. So, what do we want to prove? We want to prove that leaf size of chi sorry, leaf size of phi is greater than this. So, let us take this. So, leaf size of phi. So, phi is a formula which means it is a tree, and how does the formula look like? The formula has an AND gate at the top and there are two sub formula, right, psi and chi. Okay. So, what can I say about the leaf size of phi in terms of the leaf size of psi and chi? It is just the addition, it is the total number of leaves, right. The total number of leaves in the entire tree is the number of leaves in this subtree and this subtree. So, it is equal to leaf size of psi plus leaf size of chi, and by induction what we have is that this quantity is greater than or equal to, now I can use my notations, n psi square divided by a psi times b plus n chi square divided by a chi times b. Okay. So, this follows by induction. Now, let us try to expand this out. So, because I just decided to split it in terms of A, that is all. I am just taking this and I am just deciding to split it in terms of A over here, that is why B remains same. So, I had a notation I think. So, let me just so that it becomes a little simpler, let me just keep one more notation over here. Let small a of psi be size of this set and small a chi be size of this. Okay. So, therefore, I can write this as small a psi times small a chi. Okay. So, if we expand this out, we get n psi square a chi plus n chi square a psi divided by size of b times a psi times a chi, and let me also multiply both numerator and denominator with a psi plus a chi. Okay. And once again we expand this out, we expand the numerator. So, if we expand the numerator we get n psi square a psi a chi plus n chi square a psi a chi plus n psi square a chi square plus n chi square a psi square whole divided by b a psi a chi a psi plus a chi. Okay. Now, look at this term over here. Okay. Look at this particular term over here. Okay. So, what can I say about this term? So, what we can say is that this term is actually greater than or equal to twice n psi n chi a psi a chi. How does this hold? Huh? Exactly. Okay. So, I can take this as let us say a term x and I take consider this as my term y. So, x minus y whole square is nothing but this minus this, and x minus whole square is always greater than or equal to 0. Okay. So, using that inequality we get this result. So, now I can write this as this quantity is greater than or equal to okay, fine, let me write this out, n psi square a psi a chi plus n chi square a psi a chi plus twice n psi n chi a psi a chi divided by b okay. Now, I take a psi a chi as common and what I get is n psi plus n chi whole square divided by b times a psi plus a chi, and this is nothing but we can just substitute n a b square divided by this is a and this is b. So, a times b. Okay. So, this completes the proof. And Now, what happens if we have OR over here instead of AND? So, if I have OR over here, so instead of union over here, I will have intersection, here I will have union, and I can decide to partition B instead, and I get the same argument. Okay. So, case 3, if phi is equal to psi or chi, similar argument holds. Okay. So, this completes the proof. Now, why is this theorem interesting? How does it give a lower bound on the formula size?